What aspect of 5G that you have learned about so far has made the deepest impression on you? I think most of our partners think that the three application scenarios, EMBB, URLLC, and MMTC. The ITU's vision for these three scenarios includes a 10 gigabit per second peak rate, end-to-end latency that doesn't exceed 1 millisecond, and connectivity that includes 1 million connections in every square kilometer. To achieve these three goals, 5G networks will need some new technologies. We need new technologies to increase the 5G data rate, new technologies to reduce latency, and new technologies to increase the number of connections possible at any one time. We also need to consider that 5G uses high-frequency bands, so the coverage is limited. We will need new technologies to enhance 5G coverage. In the currently frozen R15 version, no standard MMTC scenarios have been defined. That is, the key technologies that will be used to increase the number of system connections have not been frozen. Therefore, we will focus on the three key technologies that have been frozen. The technologies used to enhance coverage, to improve rates, and to reduce delay. Shannon's theorem tells us the maximum capacity at which information can be transmitted over a communications channel of a specified bandwidth in a presence of noise. From the formula defined by this theorem, C equals B times log 2, 1 plus S divided by N, we can see that increasing the bandwidth, B, is the most direct way to increase the capacity and the transmission rate of the link. This is like increasing the traffic capacity of a road by increasing its width. 5G will be able to deliver up to a gigahertz of bandwidth. With all the bandwidth that is already allocated today, 5G will have to rely on high-frequency bands. However, high-frequency band has two major disadvantages compared to the lower-frequency band. The first disadvantage is that there is more path loss. There is less signal diffraction, so the signals have a harder time getting around obstacles. For any given transmission distance, the path loss for high-frequency signals is much higher than that for low-frequency signals. This means that the area that can be covered by a cell operating on high-frequency band is significantly less than what would be possible when working on a lower-frequency band. The second disadvantage is that the uplink and downlink coverage that can be provided is unbalanced. The higher the frequency band, the more significant the difference is between the uplink and downlink coverage. The uplink coverage is always worse than that in the downlink. The transmit power of a G node B is much greater than that of a mobile phone. As a result, the range of the PUSCH is far less than that of a downlink channel like the PDSCH. As a result, signals transmitted from a mobile phone to a cell edge may not be able to reach the base station. To address these challenges, Huawei has proposed an uplink and downlink decoupling solution. With NR, G-Node Bs use high-frequency bands to communicate with each other in the downlink. But for uplink transmissions from the UEs, a base station can make use of the lower-frequency LTE resources. For a UE near the cell center, high-frequency band is still used in the uplink, but at the cell edge, lower-frequency band can be used, which improves uplink coverage. This is what we mean by uplink and downlink decoupling. Next, let's learn about another key technology, a technology used to improve data rates. 5G provides a much higher data rate than 4G. There are many new technologies that make this possible, technologies like new coding techniques and massive MIMO. Let's start with coding. So, what is coding? In simple terms, coding is how we protect transmitted data by adding redundant bits. This redundancy makes the transmission more reliable. Imagine you bought a porcelain vase on the internet. To prevent the porcelain from being damaged during delivery, a lot of additional foam packaging is added. The coding process is a bit like this. The more padding is added, the more likely your package is to arrive in one piece. But by adding all that filler, you can also increase the size of your package, and it becomes more expensive to ship. According to the latest Frozen protocol, 3GPP Release 15, in a 5G eMBB scenario, the control channel uses polar codes, but the traffic channel uses a low-density parity check, or LDPC for short. These two coding schemes have many advantages over the turbo codes used on the 4G network. LDPC delivers better decoding performance, results in less decoding delay, and uses less power. For any given signal-to-noise ratio, polar codes result in a lower bit error rate. LDPC and polar coding have high coding efficiency. With our porcelain vase in the styrofoam packaging from before, you can protect your vase better by adding more packaging, but the package gets bigger too. This is what we mean by efficiency, more protection from the same amount of packaging. LDPC and polar encoding require less redundant data to protect your transmitted or received data. This improved efficiency allows for a better peak data rate for the end user. Now, let's take a look at a second technology used to increase our data rates: Massive MIMO. What is Massive MIMO? As the name suggests, a massive number of antennas are combined, as many as 64 in a single array, for 64T64R transmission and reception. Massive MIMO uses a large-scale antenna array for three-dimensional beamforming for multi-user resource reuse. It improves both coverage and capacity. It's sort of like the wireless routers we use at home. You may have noticed that the newer wireless routers have more antennas, and these new multi-antenna routers provide better signals and faster rates. So what are the advantages of Massive MIMO? Massive MIMO provides more data streams than can be provided in a traditional 4G 8T8R antenna array, and Massive MIMO can use 3D beamforming. In a traditional 8T8R setup, there are only 4 beams in the downlink. But with 64T64R Massive MIMO antenna array, the beams are narrower, which makes it possible to create 16 different streams. This means that at any given moment, the G-Node B can allocate the same time frequency resources to 16 different users, thereby vastly improving the overall capacity of the cell. In addition, Massive MIMO beams can also provide 3D coverage. Both horizontal and vertical beams can be created, which significantly improves the coverage for high-rise residencies or hotels. And now, let's move on to our third and final new type of technology: technologies that reduce delay. We know that one application scenario for 5G is URLLC, ultra-reliable and low-latency communications. Under ideal conditions, the end-to-end latency can be as low as 1 millisecond. This is far lower than the standard 10 milliseconds we get with 4G. So, is 5G able to deliver such low latency? Once again, we have a large number of new technologies to thank. Technologies like grant-free scheduling and device-to-device communications. First, let's look at grant-free scheduling. Normally, when your cell phone transmits data to the base station, the mobile phone first needs to send a scheduling request. The base station then sends a scheduling grant to the phone, and then, only after the phone has received the grant, can it start transmitting the data to the base station. When grant-free scheduling is used, if a phone needs to transmit data to the base station, the phone does not need to send a scheduling request. It can transmit the data directly to the base station using a pre-reserved resource block. When you compare the two processes illustrated here, it is pretty clear why grant-free scheduling has less delay. There is no time being spent on the request and authorization processes. This technology is expected to be frozen in R16. It is mainly used for delay-sensitive URLLC scenarios. Another technology used to reduce latency is device-to-device communications, or just D2D for short. What is D2D? D2D is when one device communicates directly with another device. Common D2D applications include Bluetooth, Wi-Fi Direct, walkie-talkies, and the like. However, the D2D we're talking about here refers to a technology where spectrum is allocated by a base station, a direct connection between terminals to transmit user-plane data. D2D has the following advantages. The transmission range is long and the transmission delay is small. For D2D is longer than a Bluetooth connection or a walkie-talkie. It can keep two devices connected over a kilometer or more. And transmission delay is small. D2D transmissions do not need to be relayed by a G-Node B. The two mobile phones can communicate with each other directly. This means the transmission distance can be shorter, which in turn means less transmission delay. High spectral efficiency. A D2D terminal reuses the spectrum resources of the cell, so the spectrum efficiency of the cell is improved. So now you can see how D2D technology can reduce a delay. This technology is expected to be frozen in 3GPP Release 16. This lesson has described key technologies used on the 5G air interface. Uplink and downlink decoupling enhances the 5G uplink coverage. New coding technologies, along with massive MIMO, increase the peak data rates. And the delay on a 5G network can be reduced by using grant-free scheduling and the D2D transmission. In the next lesson, we will learn about 5G spectrum planning.